In this video, we're going to cover sections 3.5 and 3.6. 3.5 discusses solvating effects and counterions and their effect on pKa values. And 3.6 will introduce Lewis acids and bases. So as we saw in the last video, we typically use the ARIO system to determine the relative acidity of organic compounds. In some cases, solvent effects can be used to explain small differences in pKa values. And so we'll use this example of tertiary butanol and ethanol to explain why seemingly similar structures, they're both alcohols and they're both small molecules, but why such a significant difference in the pKa value between seemingly similar molecules? Now, the difference in acidity of tertiary butanol versus that of ethanol has to do with the relative stability of the conjugate base. And the conjugate base of tertiary butanol is less stable than the conjugate base of ethanol due to their respective interactions with surrounding solvent molecules. As you can see in this figure, the tertiary butoxide ion is quite bulky or sterically hindered, and as a result, it's less capable of interacting with solvent, whereas the ethoxide ion is not as sterically hindered, and so it can accommodate more solvent interactions. So because of this enhanced solvent interactions with the ethoxide, because it's better solvated, it's more stable than the corresponding tertiary butoxide ion. And so because the ethoxide ion is better solvated, it is going to be more stable, and the corresponding acid, the ethanol, is going to be a stronger acid than tertiary butanol. Now, the last point I'd like to make in this particular section is with respect to counterions. We'll be using bases in various ways in the coming sections as reagents to carry out deprotonation or proton transfer reactions. These negatively charged bases are always accompanied by positively charged species, and we call these species cations. Now, it's important to recognize that in general, these cations do not play a significant role in reactions. And so you can see in this example where we have sodium amide reacting with water, the net products of this reaction are the formation of ammonia and sodium hydroxide. Now, the reason for carrying out this reaction will most likely be to form ammonia, and so we'll often consider these particular species as side products. Nonetheless, when we mix sodium amide with water, the active species is the amide ion, because recall, the differences in electronegativity between sodium and nitrogen are quite different, so this is really an ionic salt or a salt. And so in solution, this will dissociate quite readily, leaving you with the amide ion, to the point we typically don't show the sodium cation present in our reaction mechanism. Given that the sodium amide ion is the active species, we see here in our reaction mechanism that the lone pair of nitrogen is used to deprotonate one of the hydrogens on this water molecule, and in doing so generates the hydroxide ion as well. And again, we could draw in the sodium cation as being a part of this mechanism, but again, we often refer to these counterions, these cations, as being spectator ions. They're not essential to the reaction that we are observing, but more or less found in our overall reaction mixture. And so in general, we do not even show the presence of these cations when drawing our reaction mechanisms. In this next section, 3.6, we're discussing and introducing Lewis acids and bases. This is another definition used to describe acids and bases, different from the Bronsted-Lowry definition, which only involves proton donors and proton acceptors. The Lewis definition of acids and bases is much broader. So according to the Lewis definition, acidity and basicity are described in terms of electrons rather than protons. So a Lewis acid is a compound capable of functioning as an electron pair acceptor, whereas a Lewis base is a compound capable of functioning as an electron pair donor. So as you can see in our example, we have water acting as a base and hydrogen chloride acting as our acid. But we focus on the electron flow as opposed to which species is donating a proton and which species is accepting that proton. So in this Lewis definition of acids and bases, water is acting as the electron pair donor, as shown in our mechanism, and hydrogen chloride is acting as our electron pair acceptor. The net result is that we form H3O+, the hydronium ion, and we have what's left from our original acid, our conjugate base, the chloride ion. So this is how we would apply the Lewis acid-base definition to a reaction which we've seen previously using the Bronsted-Lowry definition. Now let's look at an example where we do not have a proton transfer occurring. So proton donors are not the only acids, and that's why the Lewis definition is often preferred when we talk about reactions in organic chemistry. Lewis acids can accept electron pairs through low-lying or low-energy vacant orbitals. So in this example shown below, where we have water again acting as our electron pair donor, we see here that the acid is boron trifluoride. Boron trifluoride, interesting boron species in that it has a vacant empty p orbital. Boron trifluoride, as you may recall from working on the assignment and in our class discussion, it is sp2 hybridized and has a trigonal planar geometry. It's sp2 hybridized because you can only mix orbitals that have electrons present in them. And for boron, in boron trifluoride, boron will have a half-filled s, half-filled 2p orbitals that are half-filled, but there's going to be one vacant p orbital where no electrons will be present. And so when we're hybridizing the s and the 2p orbitals of boron, we're left with 3 sp2 hybrids, leaving an empty p orbital. In this example, it's that empty p orbital on boron that is accepting that lone pair of electrons from our base, water. The net result of this interaction is we form what's known as a complex. We form this complex between the water molecule and the boron species. So as a result, Lewis acids, like boron and other elements like aluminum, these are considered electron deficient atoms because they have vacant p orbitals open for the acceptance of electron pairs. And in that way, they can act as Lewis acids when other Lewis bases, i.e. electron donors, are present. So if you have any questions on this video with respect to solvating effects, the role of counter ions, or Lewis acids and bases, send me an email or start a discussion in our forum. Thank you.